Hello, and welcome to this series of lectures on Class 10 Mathematics for CBSE Board. And let us begin with the first chapter on real numbers. So, if you recall from your Class 9, you have seen real numbers where we talked about all the different families or sets of numbers, starting with the natural numbers. The natural numbers are all numbers from 1, 2, 3, 4, and so on, all the positive numbers, not including 0. These are called as the natural numbers. And then you saw what are the whole numbers, which is the natural numbers, plus the number 0. Then you talked about the set of all integers, which included the positive natural numbers, the number 0, as well as the negative numbers. Okay, this gave us the set of integers. And then we also started to discuss about the numbers which are non-integers, so fractional numbers, and including all the positive and negative fractional numbers along with the integers. That gave us the complete set of real numbers. And within real numbers, we also talked about what are rational numbers and irrational numbers. Okay, so we had seen all of these concepts in the first chapter of Class 9. So we will be revisiting some of those topics, but for Class 10, we are going to begin with what is called as the fundamental theorem of arithmetic, and we will see how this fundamental theorem of arithmetic is applied for various mathematical problem solving. So what does this theorem state? It states that every composite number can be expressed or factorized as a product of some prime numbers, and this factorization is unique in the sense that the prime factors that we obtain for a composite number are unique, except for the order in which those prime factors are placed. So what this means is, once we see an example, it will be much clearer. So let's say we have the number 12. Okay, this number 12 is a composite number. It means that it is not a prime number. Well, so again, just to recall, what is a prime number? A prime number has only the number 1 and itself as its factors. A composite number may have other factors also other than 1 and itself. So the number 12 has factors other than 1 and 12. So some of the factors of this number are 2, 3. So we can write this as 2 into 2 into 3. So we have expressed the number 12, which is a composite number, as a product of prime numbers. So 2 is a prime number and 3 is also a prime number. So 2 into 2 is 4 and 4 into 3 is 12. So now we have expressed this as a product of prime numbers, and wherever there is a prime number repeating multiple times, we can use or express it as in terms of the powers. So we can write this as 2 power 2 into 3. So that is the prime factor representation of the number 12. Now again, you have seen how to get the prime factors of a given number in your earlier classes. So how did you get this? So you can simply keep dividing it with primes. So so you're going to divide 12 by 2. So 2 goes into 12 6 times, and then again 6 is even, so we can continue dividing it by 2. So 2 goes into 6 3 times. So now 3 can be divided only with 3 now, so that's 3 goes into 3 one time. So that we cannot divide it any further. So the prime factor representation of the number 12 is 2 into 2 into 3, which is what we had expressed here. And in a similar way, you can find the prime factors or the prime factor representation of any composite number. So what it says is, the prime factor representation of a composite number is unique. So that means the prime factors will only be 2 and 3. There will be no other prime factors for 12 other than 2 and 3. And this is unique. So this is what it means, except for the fact that the order of the prime factors can be rearranged. Okay, those may be different. So in other words, so instead of writing this as 2 power 2 into 3, we could have written this as 3 into 2 power 2. Okay, so we could have written it as 3 into 2 power 2. So 2 into 2 into 3, or 2 into 3 into 2, or 3 into 2 into 2. So either way, the order can change, but the prime factors themselves are unique. So this is what the fundamental theorem of arithmetic states. So any composite number can be expressed or factorized as a product of prime numbers, and the factorization is unique in the sense that the prime factors are unique. There will be no other prime factors other than what are there, except for the order in which we place those prime factors. Okay, so this is what we mean by this. Okay, so now it gives us a clear understanding of what the fundamental theorem of arithmetic states. So let us take one more example. So let's say we have the number 210. So we want to find the prime factors and represent the number 210 in terms of its prime factors. So since we have 210, we will proceed with the standard procedure. So we can divide it by 2. So that will be 105, and then since it's ending with 5, we have to use 5. So that will be 21 times 5 is 105, and then we have 21 now. So for 21, we can divide it with, say, 3, and we get 7, and 7 is a prime, so 7 goes into 7. Okay, so we have 2, 5, 3, and 7. So that means we can represent this as 2 into 5 into 3 into 7, or we can write this as 2 into 3 into 5 into 7. So here we are representing the prime factors in ascending order. So 2, 3, 5, 7. So you see each number is ascending. And we can write these in any order we want. So 2, 5, 3, 7, or we could have written it as 5 into 3 into 7 into 2. So it doesn't matter in which order we write it, but what we see is that the prime factors are unique. So it has the prime factors 2, 3, 5, and 7. So these are the only prime factors for the composite number 210. And this is what is meant by the uniqueness of the factorization. Of course, the order in which we are writing those factors can be changed. So that is what is mentioned here as an exception, apart from the order in which the prime factors occur. So the prime factors of 210 are 2, 3, 5, and 7. And these are unique. Okay, and this is what the fundamental theorem of arithmetic states. So we can simply state the fundamental theorem of arithmetic as follows. The prime factorization of a natural number is unique except for the order of its factors, and we have seen that with an example. So therefore, in general, we can say that given a composite number x, we can factorize that number x and represent it as a product of its prime factors. So we can write x as x equals p1 into p2 into p3 into p4 and so on up to pn, where these p1, p2, p3 up to pn are basically the prime factors. And in this particular case, if we write this in ascending order, if we write these prime numbers in ascending order, that is p1 is less than p2 is less than p3 and so on and so forth, in which case we can say that the factorization is unique. So only when the order is not specified, then the prime factors would be unique, but the orders can change. But when we have specified the order, then the factorization itself becomes unique. So if we take, for example, another number, let's say the number 32760, 32760, this can be represented as 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. So we can combine the primes which appear multiple times. So 2 into 2 into 2 is 2 power 3 into 3 is 3 square into 5 into 7 into 13. Again, how did we get these prime factors? Like we did in the previous case, you start dividing 32760 by 2, and then you see which number is divisible, it divides the resulting answer, and keep dividing it until you get the number 1 at the bottom, like we saw in the previous case, and that would give us all the prime factors. So when you divide it, make sure that you're using a prime number to divide each time. So that way you will get all the prime factors of that particular number. So basically, a given composite number x can be represented as a product of its primes, or we can also include the statement that the composite number can be represented as a product of the powers of primes. So in this case, 2 power 3, so it's a power of prime. The third power of the prime number 2, the second power of the prime number 3, and 5 power, if there's nothing here, it means 5 power 1. That means first power of the prime 5, first power of the prime 7, and first power of the prime 13. So we can state that a composite number can be represented as a product of the powers of the prime numbers. Okay, so this is in the gist of the prime factorization and the gist of the fundamental theorem of arithmetic. And this theorem has many applications that we will see, and we will solve some problems using the fundamental theorem of arithmetic. So an application of the fundamental theorem of arithmetic is in computing the HCF and LCM. So let us see how we can use the fundamental theorem of arithmetic to find the highest common factor, or HCF, by using the prime factorization. So let us consider, so we'll do the HCF first, and then we'll also do the LCM. So let us consider computing the HCF of two numbers. So let's take the two numbers as 6 and 20. So we want to compute the HCF of these two numbers. So what we do is we first write these two numbers in terms of their prime factors. So we can write 6 as 2 into 3, and we can write 20 as 2 into 2 into 5. So these are the prime factor representations of 6 and 20. And again, how to find the HCF, we have seen it in your earlier classes. So what we do is we find the factors which are common. So that's one common factor. There's no other common factor here. So the 2 and 2 appears in both the cases, in both the prime factorizations of 6 and 20. 3 appears in the factorization of 6 but not in 20. This 2 appears in the factorization of 20, but there is no further 2 in 6. And 5 appears in the factorization of 20 but not in the factorization of 6. So the HCF is the product of the common prime factors. So HCF in this case, HCF is equal to 2. So the HCF of 6 and 20 is the number 2. So in general, we can say that the HCF is the product of the smallest power of each common prime factor in the number. So the smallest power of the common prime factor. So this is 2 power 1 and this is 2 power 1. So the smallest power of each common prime factor. So 2 power 1 is common in both these factorizations. So we have only one term which is common, so we get the HCF as 2. So let us take another example here. In this case, for the numbers 96 and 404, if we want to compute the HCF, we first get the prime factor expansion of this. So 96 is 2 power 5 into 3, and 404 is 2 power 2 into 101. So the common factors in both these numbers, or the common prime factors, are so we have this 2 and this 2 is a common factor, and we have these 2's as a common factor, and there is no other term which is common. So the HCF in this case is HCF equals 2 into 2, which is 4. So the HCF of these two numbers is 2. And in terms of this general statement, it's the product of the smallest power of each common prime factor. So we could have written this 2 power 5 as 2 power 2 into 2 power 3, right? So that's 2 power 5 into 3. So that's there. And then we had for 404, it is 2 power 2 into 101. So the common prime factors with the smallest power are 2 power 2 in both these cases. So we have 2 power 2 here and 2 power 2 here. So the when we have the same prime factor, 2 appearing multiple times, in that case we take the smallest power of it. So 2 power 2, the power 2 is the smallest power in this case, which is common to both the factorizations. And if we have similar terms, suppose we had 3 power 2 also and 3 power 2 in the other one also, then we'll take those terms as well and multiply them to get the HCF. In this case, we have only one smallest power which is common to both these numbers. So the HCF is basically that single 2 power 2 term, which is the number 4. Okay, so we have seen how to calculate the HCF using the prime factorization method. And again, the prime factorization comes from the fundamental theorem of arithmetic, and this is one of the applications of the fundamental theorem of arithmetic, that is to calculate the highest common factor. Now let us see how we can calculate the LCM of some given numbers by using the prime factorization method. And let us use the same examples, 6 and 20 and 96 and 104, to find the LCM of those two numbers. So let us take the example of 6 and 20 and compute the LCM of 6 and 20. So LCM of 6 and 20. And again, what we will do is we will first represent these 6 and 20 in terms of their prime factors. So 6 is 2 into 3 and 20 is 2 into 2 into 5, which is what we had earlier. So we can write this as 2 power 1 into 3 power 1, and here we have 2 power 2 into 5 power 1. And what is the rule for finding the LCM? So the LCM is nothing but the product of the greatest power of each prime factor involved in the numbers. So we have 2 as a prime factor, and the greatest power of 2 is 2 power 2. So we will use this number, 2 power 2, in our LCM. So that is involved there. And then we have a prime factor of 3, and the greatest power of 3 is simply 3 power 1. So we will use 3 power 1. And the greatest power of 5 is 5 power 1. Okay, so within this factorization, the greatest power of 2 is 2 power 2, the greatest power of 3 is 3 power 1, and the greatest power of 5 is 1 as well. Okay, so we take the product of the greatest powers of each of the prime factors, and that gives us the LCM. So therefore we will have the LCM of 6 and 20 as 2 power 2 into 3 power 1 into 5 power 1, which is nothing but 4 into 3. Let me write that clearly. 4 into 3 into 5. So that is basically 60. So the LCM of 6 and 20 is 60. So coming to the LCM of 96 and 404, the prime factorization of 96 is 2 power 5 into 3, and the prime factorization of 404 is 2 power 2 into 101. So the LCM in this case is going to be LCM equals the greatest power of each prime factor. So for the prime factor 2, the greatest power in this factorization is 2 power 5. So we will take only the greatest power. So 2 power 5 is one of the terms that we are going to have. So LCM is the product of the greatest power of each prime factor that appears in the factorization. So 2 power 5, and for the number 3, the greatest power is 3 power 1. So we will use that as well. So that will be 3 power 1. If there is no power there, it means 3 power 1. And then for 101, it means it's 101 power 1. So the LCM is going to be 2 power 5 into 3 power 1 into 101 power 1, which is 2 power 5 into 3 into 101, which gives us an answer of 9696. So this product is equal to 9696. Okay, so now remember the difference between LCM and HCF. When we did the HCF, we are looking for the common terms. Okay, so the smallest power that is common to both the terms. So see, I've underlined the word common here. But in the case of LCM, we are not looking for common terms, but we are simply looking for the greatest power that occurs for a given prime factor in the factorization, and we take those greatest powers of a particular prime factor and multiply them to get the LCM. So 2 power 5 is the greatest power of 2 in both these factorizations. 3 power 1 is the greatest power of 3 in both the factorizations, and 3 is not common to both. And similarly, 101 power 1 is the greatest prime factor which is involved in these factorizations. And again, there is no commonality between of 101 in these two factorizations. So for LCM, we don't worry about the factor being common, but for HCF, it is important to make sure that the factor or the power of the factor is common, and we take the smallest power here. But whereas for the LCM, we take the largest power, but we did not worry about that factor being common to both the terms. So in general, we can state this rule for LCM using the prime factors as the LCM is nothing but the product of the greatest power of each prime factor that is involved in those numbers. So you don't see the word common here in this definition as compared to the HCF, where we have the common word. Okay, it's the common prime factor with the smallest power. So let me underline smallest as well here. So for HCF, it is the smallest power which is common to both the numbers, whereas for the LCM, it is the product of the greatest power, but it need not, we don't worry about that greatest power being common to both the numbers. Okay, so LCM is the product of the greatest power of each of the prime factors that are involved in the number. So the prime factor 2, the greatest power of 2 is 2 in this case, the greatest power of 3 is 1, and the greatest power of 5 is also 1. So we take the greatest powers and multiply them all together, and that gives us the LCM. Okay, now that we have computed the HCF and LCM of two numbers, in this case for 6 and 20, so if you notice, the HCF of 6 and 20, we got it as 2, and the LCM of 6 and 20, we got it as 60. And one observation that we can make is that if we look for HCF of 6 and 20, we got it as 2, so let me write that down. HCF of 6 and 20 equals 2, and LCM of 6 and 20 is 60. And what we notice here is that the product of the HCF and LCM, so HCF into LCM, which is 2 into 60, which is 120. And 120 also happens to be the product of 6 and 20, that is equal to 6 into 20, which is also 120. So what we see is that the product of the HCF and LCM of two numbers is equal to the product of those two numbers. So let's verify whether it's true for the second example of the HCF and LCM for 96 and 404. So the HCF of 96 and 404 is 4, and the LCM is 9696. So from the previous page we got HCF as 4, and the product of HCF and LCM, HCF into LCM, is going to be 4 into 9696, and that is equal to, and we get that product of HCF and LCM as 38784, which is the same as the product of 96 and 404, that is also equal to 38784. So one of the use of this relationship is that if you're asked to find the HCF and LCM of two numbers, once we have computed the HCF, calculating the LCM, we need not go through the process of calculating the LCM. We can use this relationship to find the LCM if we know the HCF, or if we know the LCM, we can find the HCF by using the relationship. So in general, we can write this relationship as follows. So for two numbers A and B, HCF of two numbers A comma B, so if we can consider two numbers A and B, the product of the HCF of A and B and the LCM of A and B is equal to the product of the two numbers itself, is equal to A into B. So if we know the HCF of the two numbers, we can find the LCM as LCM equals A into B divided by HCF, right? So we can write LCM equals A into B divided by HCF, or we can write HCF equals A into B divided by LCM. Okay, so if we know the LCM, we can find the HCF, and if we know the HCF, we can find the LCM. However, be careful that this rule applies only to the LCM and HCF of two numbers. Okay, if we have more than two numbers, then this rule does not apply, as we will see with an example now. So let us consider the case of the HCF and LCM of three numbers, and we will check whether the product rule applies here or not. So let's consider three numbers and find the HCF of those three numbers. So HCF of 6, 72, and 120. Okay, so to find the HCF, we will write first of all each of these numbers in terms of their prime factors. So 6 is 2 into 3. 72 can be written as 2 into 2 into 2 into 3 into 3. Okay, and 120 can be written as 2 into 2 into 2 into 3 into 5. Okay, so basically this is we can write this as 2 2 power 1 into 3 power 1. So this is 2 power 3 into 3 power 2, and this is 2 power 3 into 3 power 1 into 5 power 1. Okay, so we have now written down these prime factors in terms of the power. So 2 into 2 into 2 is 2 power 3, and 3 into 3 is 3 square. So similarly here, 2 into 2 into 2 is 2 power 3, and this is 3 power 1 and 5 power 1. So to find the HCF, we take the product of the smallest power of the prime factor, which is common in all the terms. So to find the smallest power, so I just rewritten this 2 power 3 here as 2 power 1 into 2 power 2. So that's 2 power 3. Similarly, 3 power 2 is written as 3 power 1 into 3 power 1. So we basically split this. So now we will find the smallest power of a prime factor which is common in all the terms, in all the prime factors of the three numbers. So let me use a different color here. So this 2 power 1 is the smallest power of 2 that is common in the prime factorization of all the three numbers. Similarly, 3 power 1 is the smallest power of 3 that is common to all the three numbers. And there is no other smallest power of prime factor that is common to all the three numbers. So we have this 3 power 1 in the second number in 72, but it is not available in 120 or 6. Similarly, 5 power 1 is available in 120 but not in 72 and 6. So we are left with the common terms, which is 2 power 1 and 3 power 1. So that will give us the HCF value, HCF, as 2 power 1 into 3 power 1, which is basically 2 into 3, which is 6. Okay, and from your earlier classes, when you studied class 9, you would have done it like this. So without using the powers, so you would have taken only the common terms here. So that 2 is a common term, and then this 3 is a common term here, right? So 2 into 3 is 6, which is what we have obtained here. But now we have used the definition of the powers. Okay, the smallest power of the factor, prime factor, that is common to all the numbers, and we multiply that prime factor with the smallest power, okay, which is common to all the numbers for which we are computing the HCF. Okay, so we have got the HCF of these three numbers. Similarly, let's move on to compute the LCM. So to find the LCM of 6, 72 and 120, again we are going to write them in terms of their prime factors. So 6 is 2 into 3, and 72 is 2 into 2 into 2 into 3 into 3, and 120 is 2 into 2 into 2 into 3 into 5. And in this case, we are going to in writing them in terms of the powers. It's 2 power 1 into 3 power 1, and this is 2 power 3 into 3 power 2, and this is 2 power 3 into 3 power 1 into 5 power 1. So we are now going to compute the LCM, and for the purposes of the LCM, we have to take the highest power of each of the prime factors that occurs in each of the prime factorizations. So the prime factors involved in all the three numbers are 2, 3, and 5. So the highest power of 2 that occurs in the prime factorization of the three numbers is 2 power 3. So we have 2 power 3, 2 power 3 in 72 and 120. So the highest factor that is 2 power 3, and we take it only once. Okay, whatever is the highest, we take it only once. So we will take one of those 2 power 3s. So let's say I'm choosing any one at random, so I'll choose this one, 2 power 3. So the highest power of 3 is 3 power 2, and the highest power of 5 is 5 power 1. Okay, so again, for LCM, we need not worry that these factors are common to all the three terms or not, but we only choose the highest power of each of the prime factors that occurs in the expansion of those numbers. So the LCM is simply LCM equals 2 power 3 into 3 squared, that's 3 power 2 into 5 power 1, which is simply 5. So 2 power 3 is 8, 3 square is 9, so it's 8 into 9 is 720, 8 into 9 is 72, and 72 into 5 is equal to 360. So we get the LCM as 360. And now let's see whether the product of the HCF and LCM of these three numbers is equal to the product of those three numbers. So in this case, let me make a little partition here. So HCF into LCM is 6 into 360, and 6 into 360 is equal to 2160. So the product of the HCF and LCM of these three numbers is 2160, and the product of the numbers itself is 6 into 72 into 120, and that is equal to 51840. That's 51,840. Clearly, you see that HCF into LCM of these three numbers, let me be very precise here. HCF of 6, 72 and 120 into LCM of 6, 72 and 120, and this product is not equal to 6 into 72 into 120, right? So this relationship between HCF, LCM and the product of the numbers applies only when we are doing the HCF and LCM of two numbers. If it is more than two numbers, then that rule does not apply. Okay, so you have to be careful. So if it is more than two numbers, then that rule does not apply. If it is only two numbers for which we are computing the product, computing the HCF and LCM, then the product of HCF and LCM of two numbers is equal to the product of those two numbers itself. If it is for more than two numbers, then the product of HCF and LCM is not equal to the product of those more than two numbers. Okay, so now we have seen HCF and LCM and how the fundamental theorem of arithmetic is used in computing the HCF and LCM of numbers. Let us move on to another example of the application of the fundamental theorem of arithmetic, and that deals with seeing whether a certain pattern of numbers satisfied certain properties or not. For example, let's see if we have a number, a set of numbers denoted by 4 power n, okay, where n is a natural number. That means n is 1, 2, 3, 4, and so on and so forth. And what we are asked is to check whether there is any value of n for which 4 power n results in an answer whose last digit, which is the ones digit, is 0. So that means whether 4 power n results in a number that ends in the digit 0. So we are asked to check whether there is any n for which this such a number can be achieved. So how do we check? Okay, there are infinite possibilities of n. So we can have 4 power 1, 4 power 2, 4 power 3, 4 power 4, 4 power 5, and so on up to infinity. So how can we check and be sure that none of the values of n will result in 4 power n in a number that ends with the digit 0. So how to do that? How to verify that? Or if at all there is some number that exists where for n that gives an answer of 4 power n which ends in a 0. So how to check this? And the fundamental theorem of arithmetic, which talks about the prime factorization, that helps us in solving such kind of problems. So we can write this number 4 power n as 2 power 2n, right? So 4 is nothing but, okay, let me write one more step there. 4 is nothing but 2 square, right? So it's 4 power n is nothing but 2 square power n, and we can write this as 2 power 2n. So the only prime factor that is present in the expansion of any number 4 power n for any value of n is the number 2. So all the prime factors of any 4 power n is going to be 2. So it is going to be 2 power something. Okay, so 4 power 1 is 2 power 2, 4 power 2 is 2 power 4, 4 power 3 is 2 power 6. So that means the prime factorization of 4 power n will involve only a single prime factor, which is the number 2. Now, if any 4 power n ends with the digit 0, then the prime factor must include the number 5, because any number that ends with the digit 0 must be divisible by 5. So therefore, one of the prime factors for that number should be a 5. So since there is no prime factor of 5 here, we can say that none of the numbers of the pattern of 4 power n for any natural number n will end in the digit 0. Okay, so we say that if 4 power n ends in 0, 5 must be one of the prime factors. Okay, however, for 4 power n, there is no prime factor of 5. For any 4 power n, the only prime factor that is involved is the number 2. Since the only prime factor in 4 power n is 2, 4 power n cannot end in the digit 0 for any value of n. So there is no value of n that will give us 4 power n that results in the last digit being 0. Okay, that ends in the digit 0. So we can use the fundamental theorem of arithmetic using the factorization, prime factorization, to determine whether a given pattern of numbers satisfies certain condition or not. In this case, the condition we are looking for is whether the pattern of numbers of the pattern 4 power n will have a digit 0 as the last digit. Whether there will be any number for any value of n that ends in a digit 0. Okay, and we see that since 5 is never going to be a prime factor for 4 power n, so none of the values of 4 power n will ever end in the last digit as 0. Okay, so we have seen much of the topics related to the fundamental theorem of arithmetic, and we have seen some applications of how to use the fundamental theorem of arithmetic. And I'll stop here for now, and we will continue in the next lecture. We will do some exercise problems based on the fundamental theorem of arithmetic, which is going to be exercise 1.1 from the textbook. So I will be solving some sample questions from that exercise and leave some other problems for you to practice by yourself. Okay, we'll continue in the next lecture with exercise 1.1.